Yeah. Dr. Hill, I think, left off talking about, Dr. Professor guy, that dude left off talking about acid-catalyzed hydration, right? I think so. I just wanted to recap that mechanism. I feel like he maybe broke it down a little bit weird, but it always helps to see it explained two different ways. So he used cyclohex, or cyclopentane. Shit, whatever, I'll do that too. That's what I started with. And you've got this reacting with, we've got some H plus in the mix, and some H2SO4, H2O. Yeah, H plus, really H2SO4. But this sulfate ion is not really going to participate too much. We can really think of this as just chaperoning in these protons, which are going to help us with our rad protonations and deprotonations. And so Dr. Hill started by identifying our alkene as a Lewis base, which is completely correct. Is a Lewis base. We have to remember that Lewis bases donate electrons.
Is that the same as a nucleophile?
Yes, it's exactly what I was going to get to. It is the same as a nucleophile. It is also a nucleophile. So Lewis bases are, well, yeah, nucleophiles. I prefer to use the term nucleophile to identify, so called this guy our Lewis acid. The proton is our Lewis acid. And I prefer to call them the nucleophile and electrophile. I find that language to be a little bit less confusing, so that we can separate this discussion from acidity and basicity. Though they are really the same, but at our level, I think it helps to keep them separate. Yeah, so we don't mix up nucleophiles and Bronsted bases, for example. So anyway, this reaction starts, we identify our nucleophile / Lewis base as the alkene, and this is because it has the double bond. We have to remember that double bonds are going to be good nucleophiles. There's an abundance of electrons, and they're also, part of the reason why they're really dope is, just do a doodle, where's my screen end? Ends around here. So the double bond is flat. So if this bond's coming out at us, no one's going away. This one's coming out at us. And its pi orbitals are above the double bond. Oh, a bunch of electrons. And below the double bond. And so since this is flat, it's very easy for these electrons to be accessed / to attack stuff. It's totally flat, and you have to come in from the bottom or top. There's not going to be a lot of crap in your way. So that's part of the reason why double bonds are real tight nucleophiles. Get out of here, sketcheroo of garbage. Cool, so our nucleophile attacks our electrophile with its electrons. We're going to use the curved arrow. It comes from our source of electrons, which is the double bond. In other examples, it will come from a specific atom's lone pair or an atom itself, but here our electrons come out of the double bond and they flow to our electrophile. And so this causes the double bond to break. Those electrons have left that bonding site, and they form a new bond with the hydrogen. And that's only one of these carbons can form a bond with this hydrogen, because as we know, hydrogen can only form one bond. So let's get in our pre-existing hydrogens. We have those to begin with, and we'll put the hydrogen on our top atom, top carbon. In this case, it doesn't matter where I put this hydrogen. but it will matter in other examples, which we'll talk about. Right, so this carbon down here now has lost electrons that it was hanging out with. It was sharing electrons in this double bond, and since it no longer has access to those, it takes on a positive charge. The other way we can rationalize that it should have a positive charge is because if we look at the total charge, or the charge balance, in our first step of the reaction, we said we have a positively charged proton, water, and a double bond. The overall charge here of all of our species is +1. In our second step, we should still have an overall charge of +1 because we're not introducing any other charges, and we have to maintain the same charge throughout a reaction. We can't just like poof magically create electrons or destroy protons. It kind of comes in with conservation of matter. So over here, we still have our water. That hasn't done anything yet. And we still have an overall charge of +1. And for this reaction, the conditions that we run this in, I didn't really write them up here, but this is run in water. Water is our solvent. So we can really use infinite waters. We can pop them in and out of our reaction as we need to, because there's a bajillion of them floating around relative to the number of our molecule, or our substrate, the molecule we're doing the reaction on. Anyway, so we form this dope carbocation. Doesn't matter where we put it because of this molecule. In the future it will. We'll talk about that. So we've now got this intermediate species. And we also have changed up. This was before a nucleophile. This is our electrophile. But now, since we have a carbocation, since what the carbocation is really is a vacant p orbital, it's like a p orbital here, and it's empty and desperate for electrons. This is now a really awesome, I'm going to get that p orbital out of there because it looks confusing. This is now a very good electrophile. And when we have a very, very good electrophile, we can get a crappy nucleophile to do an attack. And so we have this water that we're running the reaction. Water is not a super rad nucleophile, but when it's presented with a kick-ass electrophile, like a carbocation, it can attack that carbocation with the lone pair of electrons. And so these are the really badass steps in this reaction. Dr. Face described this as a three-step reaction, which it is, but the last step is really pretty meh compared to the first two. So after this attack, we have two nucleophilic attacks that occur. The first we could really consider to be a proton transfer, I suppose, but I think of that as a nucleophilic attack. We've now formed a bond between this carbon and this oxygen. It still has both of its H's on it, and as a result, it has a positive charge. So our last step is going to be getting back to a neutrally charged molecule. Shazam! And so another friendly water molecule who's in solution flies in and can scoop that up. Or if we're running this reaction in a H2SO4, you could alternatively show a friendly deprotonated, an HSO4 minus doing the deprotonation. Either way, you have to deprotonate and kick that electron back onto that oxygen to make it nice and happy and neutrally charged. So, three-step reaction, and it's not too bad if you can look at the first two reagents, or the first set of reagents, and say, who here is a nucleophile and who is an electrophile? Who's going to attack whom? The nucleophile, you see the double bond, you should be like, oh yeah, motherfucking nucleophile, get that. And presented with water and a proton, it's definitely going to attack the proton first, because the proton's a way doper electrophile. Then this generates the carbocation. And so a carbocation is a kick-ass electrophile again. So it will react with any nucleophiles around it. And we just so happen to have this water all around it, since the reaction is essentially run in water. So the water behaves as a nucleophile now and attacks. As long as, yeah. And then our last step, pretty much any time if we form a product, if we form a reactant or intermediate that looks like our product but is protonated, our last step is going to be a deprotonation. These are very common final deprotonation steps.
I'm a little confused by the last step.
The last step? Yeah, let me get this extraneous guy out of here.
Is that not needed?
That was not needed. Sorry, yeah. I drew in 2 examples. And yeah, thank you for asking about that. So I would show water doing the deprotonation, I think.
So the one water, one molecule water attaches to the carbocation, and another one just attaches to the other water, and they just...
Another one, the other one, so let me draw the final product. So this last one, this second water molecule I've used is just going to remove this extra proton from this OH group. Cool?
Mm-hmm.
Does that make sense? So yeah, so then we generate the hydrogens up here, OH, H, and we have an H3O plus. Yay! Does that clarify?
Yeah.
Are there any other questions? You guys have any other preguntas?
Just if it were the acid that you put up, would we just add the H onto that acid then?
Yes.
Okay.
Yeah, if you showed the acid doing the deprotonation step, then you would just have H2SO4. I would use water though.
Okay.
Yeah,
Well,
based on...
does he give us that choice? Or
well, the way he showed it, he didn't use H2SO4 at all. So I would follow the way he did it, and yeah. Whenever I see H2SO4, I just treat this as being H+, which is, when in water, really the same thing as H3O+. So we start with H3O+, and we end with H3O+. That's why we call it catalytic in this sense. It just helps the reaction along. If we did this without the H3O+, we'd have to it would happen, but not readily. You really have to cook that stuff in forever. Dr. Hill briefly mentioned that this polymerizes, which is something that's kind of worth mentioning. In case he asks about it. So what can also happen here when we form this carbocation, what do you guys think would happen if this intermediate ran into one of these starting materials, a molecule's starting material? What do you folks think would happen if these two molecules came together? For starters, do we have a nucleophile and an electrophile?
We do have a nucleophile.
Right? Who's the nucleophile?
So the one above it, the double bond.
Double bond is our nucleophile, right? Just like before, it's still a nucleophile. And this we said is a really tight carbocation, real tight electrophile. It wants electrons real bad. So what can happen is our nucleophile, our starting material, can attack this intermediate, this carbocation intermediate. So let's think, what would that look like? Well, we'll treat it the same way we did as our first step, because that's really the same way we should treat all of these interactions.
No bonds are going to go for to attack the carbon in the middle, on the bottom?
Right. Our double bond electrons are going to attack the carbocation. So what kind of product is this going to give us? Well, let's start by drawing this dude, because that molecule hasn't changed, except we're now going to generate a carbon-carbon bond off of this. So let's start with, we'll call this guy ring A, and this one B. Start with ring A, has its 2 hydrogens up here, it has a hydrogen there, and we've now made a bond to ring B. And like we said before, it doesn't matter terribly which carbon gets the attachment, because this is a symmetric, it's evenly substituted. If it weren't, you'd have a different picture. So I'm just going to make it attached to this guy. Just draw a 5-membered ring in. And so we should now have a carbocation on ring B. So we've polymerized, we've taken a monomer, and now we've made a dimer. 2 of the same molecule connected. And this can happen continuously. This can just keep going forward and being like, oh, what's that? Another double bond? Mwahaha. Oh wait, I drew that. I was going to draw my arrow the wrong way. The electrophile gets attacked. The electrophile does not do the attacking. Another double bond can be attacked, or attack this carbocation, and we can continually screw up our reactions. So that's why this reaction kind of sucks. Dr. Hill did say that it sucks. So that's the polymerization. It is a regio-specific reaction. You know what? I meant to look up a nice definition of regio-specific. Where did I leave my textbook in here and it like got stolen?
I have it. Yeah, he was using it.
Oh, you were looking
I
at
was
it?
using it, yeah. I don't know whose it was, but...
Oh yeah, it's mine.
I was using it. I didn't... I put it in here.
That's cool. Just want to look up a nice textbook definition because I was having trouble putting it into words earlier. So let's memorize this. Textbook, you kind of suck in the binder. So give me that regiochemistry. Okay, just discussing constitutional isomers. Yeah, that makes sense. So yeah. So this reaction, the catalytic or H+ catalyzed hydration, adding water to that joint, is regiospecific. And what does regiospecific mean? Oh my gosh, it means that we're going to, reaction has a preference for one constitutional isomer. I can't spell isomer. Isomer which may be formed. That's not what the book said. Maybe I should read what the book said exactly. Reaction that can produce 2 or more constitutional isomer but nevertheless produces 1 as a major product. That's way better. Reaction that produces 2 or more constitutional isomers has preference for 1. So, how does that relate to what we're talking about right now? For us, when we're looking at let's use this super simple molecule as an example, this 2-methyl to butene. If we were to react to this with a little bit of acid and water, there's two potential products that we can form, right? This initial attack could land our hydrogen. Let's put this guy in there too. Oh, we got rid of our double bond. This could give us either, I'll draw the intermediate, the carbocation here, and our hydrogen is placed in the disubstituted center. Or we could have the hydrogen on the monosubstituted side of our alkene and get this potential product, or not product, intermediate. So the difference is where our carbocation is located. So do you guys think the one on top is higher energy or bottom is higher energy? Bottom?
Bottom's the one that we want to do.
Yes, bottom is the one that we want. Why is that?
Because it has higher degrees of unsaturation.
Steric interaction.
It is a higher degrees of unsaturation, correct. Unsaturation, yes. Unsaturation, or the way I think about it
Is
is...
that 2 methyl groups on the end? Is that what that is?
Yes, those are methyl
Oh,
groups.
okay. And there's 2 H's on the right.
Yeah.
That would get the other one beyond energy.
So the way I consider this, but higher degrees of unsaturation is totally correct the way I think about it personally.
Tertiary, right?
Yes, I look at this as being a more substituted carbocation, which is really the same thing you said, but just different words. More substituted, higher degree of unsaturation. So we have a tertiary carbocation. There are 1, 2, 3 carbon substituents on our carbocation versus the secondary, which has 1, 2 carbon substituents on the cations. And the tertiary is more stable. So we strongly favor this intermediate. And as a result, we predominantly produce the tertiary alcohol. So this is a regioselective reaction. We have 2 potential isomers. We could also, we would probably produce a very small amount of this secondary alcohol product, but the primary product is going to be our tertiary alcohol. Yeah, this obeys that real dope dude's rule, Markovnikov. So this obeys Markovnikov's rule, which is that when we're doing an addition, we add to the more substituted side of a double bond. Did you guys go over chapter 8 at all? I feel like that didn't really happen. Making alkenes, it seems like you guys have just done chapter 9. Yeah, okay.
It's 2 lectures in chapter 8.
Huh?
There's 1.5 in lecture 8.
There was just a little bit of chapter 8.
It's like 1.5 lectures of chapter 8.
That was it though? But you're supposed to know it all?
It was just like naming, I think, like naming alkenes.
That was, yeah.
But none of the reactions to form alkenes. Cool.
I never understood what it means, more substituted.
More substituted? That's okay. Yeah, dude.
It's probably really obvious, but
I mean, the most obvious questions, though, are the hardest ones to ask. Thank you for asking that. Yeah, so more substituted. What does substitution mean? It's a word we use all the time, but we barely spend any time actually defining. I feel like that's the issue with teaching orgo. There's just so much lingo. You don't spend time talking about each term. becomes ambiguous, and then you use it twice, and you're like, yeah, they probably know what I'm talking about. No. So substituted. This just means the least substituted molecule that I can draw, really, would be a methyl, or least substituted carbon would be a methyl group. So substitution refers to us putting non-hydrogen non-H atoms on a carbon. So the more non-hydrogen attachments we have, the more substituted it is. So this is like the least substituted I can make this single carbon. And then if we put a CH3 and we put a methyl on it, right, ME, that's more substituted. Put two methyls on it, that's more substituted, etc. Most substituted would be a T, butane, butane.
Makes sense now.
Yeah, yeah, it makes sense once it's explained. Sorry, I did not do that much earlier. So. We mentioned that the reaction is regiospecific, but it's not, I'm sorry, yeah, that's regiospecific, but it's not stereospecific. Did I get into this chapter? It's annoying not knowing what order he's going to cover things in, right? Mm-hmm. It'd be really cool if it was just like, yeah, you followed the book. It was so obvious.
Can we just do stuff like it's gonna be on the test?
Huh?
Can we just do like maybe stuff from like that's previous chapters? It's gonna be on it, or because we don't know what he's gonna do.
I don't know. I just don't know what he's gonna do. It's part of the trouble of studying a text that's not being used. Let's.
The Z and E stuff, is that just like R and S?
Yeah, let's talk about that. I wanted to get into that. I have some notes about things I wanted to talk about. I did talk about.
You remember Z as Z same side?
Yeah. Z is. Oh, you remember Z is the same side?
Yeah.
So yeah, let's talk real quick about nomenclature of alkenes, and how to handle alkene names. So when we have alkenes, because they're flat, because they don't rotate, it's important what side stuff is on. We have 4 different substituents. They are not going to just readily swap places and rotate around like we would see with alkanes. So alkane bonds, single bonds, rotate readily. This don't happen. You don't have just willy-nilly rotation. And because of that, we have to name things and say, oh, this is the order of our substituents on the alkene. Because with a specific molecule, there's a specific order. So when we have one substituent, it's not a big deal. It's just part of a chain. It's at the end of a chain. If we have 2 substituents, if we have 2 substituents on the same carbon, naming's not a big deal. But if we have 2 substituents on different carbons, then we're going to use this cis-trans naming. So this one's pretty easy. Not much to it. If things are on the opposite side, we got trans, our substituents are on the opposite sides. If we have the substituents on the same side, then it's cis. Bam. Yeah. Anyway, what if we have more than 2 substituents? 3 or 4 substituents, you ask? Well, we're going to use this really neato E or Z method. So this one gets a little bit more complicated. We have to do a little bit more thinking. We can't just look and be like opposite side, same side. So the E or Z business, to do this, we're going to have to think back to our study of chirality and how we came up with priority for chirality. We're going to have to assign priority to our substituents. So first, we're going to assign priority on, and we're going to look at each carbon for this, and we're going to treat them different. So let's get an example molecule up here. Put like an iodide up there, and a CH3 there. And we'll put like bromine there, and we'll put like, somehow this is bonded with krypton, and the natural order of the world is shattering. Krypton with a bond on it, you would have a positive charge, I guess. Yeah. Maybe not. Let's not put krypton on there. That's stupid. Let's put chlorine there. So we're going to assign priority, and we're going to look at each carbon. So remember, when we're assigning priority, we look for highest molecular, or I guess atomic mass. So we compare the atoms, the substituents, based on their atomic mass. And we're looking for, if it's a carbon chain, which I'll do an example of in a second, we're looking for the, right, we're still looking at the atomic mass of the first carbon, the first element in a chain. So for this example, we look at this carbon and we say, all right, we've got bromine and chlorine. Bromine is heavier, so bromine is priority number 1. Dr. Face Dude called it high and low. I like 1 and 2, whatever. That's how I does it. Chlorine should be number 2. We look at this carbon and we say, aha, iodine, that's way heavier than carbon, number 1 and number 2. So, this one is, you guys know E or Z?
Z.
Z, right. So this is Z, which is like for Zeiten or something German. The way I always remember E and Z is because I was an idiot when I first learned it, and it was like, Z, that looks like that kind of, they should be, the highest priority things should be on opposite sides, but that system doesn't work at all. And so now I always remember, aha, Z, no, it's a trap. It's not convenient and easy based on the letter. So yeah, Z for when we have things on opposite sides. E for when we have our highest priority, I'm sorry, Z is for when we have things on our highest priority on the same side. E is for when we have highest priority on opposite sides. So let's look at a little bit more of a complicated scenario. Oh, why would... Okay, fun molecule. So much fun. Got all sorts of functional groups on here. Here we have a ketone. Here we have a nitrile. We've got a real cool ether here and a ester up there. Veritable smorgasbord of functional groups. Ester, ketone, nitrile, and ether. But that's not really what we're here to talk about. We're here to talk about the ranking of priority. So if we look at these on this side, each of these start with carbon, so we're tied. I like to draw a little diagram. So we look initially, and the priority is difficult to decide because the first atoms in each substituent are both carbons. So we have to look at what atoms those guys are attached to. So our top one has 2 bonds to oxygen and another bond to carbon. And the one below has 3 bonds to nitrogen. So our top priority one is the one that has attachments to the heaviest atoms. So the dude up top is attached to oxygen, which is heavier than nitrogen, therefore it wins. So this is our number 1 priority, this is our number 2. If we look on the other side, we have oxygen as our first atom in either case. That's then attached to a carbon in both cases, so we have to probe a little further. Our carbon up top has 2 bonds to oxygen and another bond to carbon, while down below, just some hydrogens. Oxygen and carbon are both heavier than hydrogen, so our top one is going to be top priority again. Our bottom one is lower priority, so we have them on the same side again. I should have intentionally mixed them up. That was stupid. But this is also going to be Z, yeah.
When does triple bonds take priority over double bonds? Isn't that one of the things?
That is one of the things he mentioned. So if it weren't oxygen and nitrogen in the picture, the triple bond would...
So if it were like C triple bonded to O, the bottom one would win right now?
Yes.
Okay.
It's because the oxygen is heavier
Okay.
that it trumps the nitrogen in this case. Good question. Good question. Yeah. If we did, though, well, I won't get very too deep into that. Yeah, E and Z, super effing rad. And just to go over naming them again really quick, because I think naming alkenes just at first is a little peculiar. When we're naming them, beyond just the E and Z business, we have to remember that they take priority. I could still have kept alkene names up there. They take priority in a molecule. So we could have some sort of crazy-ass long alkyl chain. It's got like substituents on it and shit. And that's attached to a chain with a double bond. You know what? We're still going to end up counting through that big crazy alkyl chain. How can I? No, I can't. I can't do this example. Never mind. But the alkene is always going to take priority. So let's leave it like that and make this dude super effing long. So that's this chain here is 12 carbons long. Normally, if you just saw this and there weren't a double bond down here, we would start by naming this main chain as a dodecane. But that's not the case because of the double bond. Because of the double bond, we're going to make sure that our longest chain that we name includes the double bond in it. So I'm going to start numbering at the double bond. Get out of here other numbers that I used just for tabulation. And go 1, 2, 3, which side's longer? I think that side is. 4, 5, 6, 8, 10, 11. So this instead will be on Undecene. And then we have to go about naming it. This one's not super duper interesting. It's got a methyl and an isopentyl on it. So this would be what? 4 isopentyl. 5 methyl undecene. And since the double bond is on the first carbon in the chain, I don't have to state where it is in the name. But it's not really a problem if you call this one undecene. It's not a problem. It just gives you a little bit of redundant information. But I don't think it's really too bad to be redundant with your information. Question? Yeah.
Is the methyl group on the other side not added?
Over there?
Oh, right now, never mind.
Because we're not counting the other chain. That would only give us 5, 6, 7, 8. Not as long of a chain. So I named this whole thing as a isopentyl group. The iso groups, pretty much we take the normal chain and chop off the carbon at the end, move it so that the end is forked with 2 methyl groups. So 1, 2, 3, 4, 5 carbons in that forked guy gives us an isopentyl. Yeah, other thoughts? So it takes priority in a molecule. If we look at it in a ring, we also see it taking priority. So if we had like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we had some giant long chain popping off of this ring. Normally, we would give priority to the giant chain because it's the biggest molecule. But in this case, again, we're going to use the part of the molecule that the hexene or the double bond is in. So this is going to be a cyclohexene. This is going to be our base name. I want to do one of these where the double bond doesn't take top priority though. So let's not even go through that, or rather where it's not, we have to number where it is. So let's look at a chain. Let's put a few double bonds in it. Yeah, that's really annoying. Let's do that. So how the F are we going to name this molecule? All right, well, we want our longest chain to include our double bonds. That's step 1. Let's figure out what the root name of our molecule will be. So our chain is 1, 3, 5, 7, 9 long. So it's a non-adiene. So it's a diene, not a regular ene suffix, because we have 2 double bonds, not 4. 2, 1 hand for each side. Cool. Not a diene. And we want our numbering for our double bonds to be as small as possible. So if we start counting in from this side, we'll have 1, 2, we hit carbon number 3. Shoot, it's the same on the other side. Let's make it 1 longer. We're making it 1 longer. It's a decadiene. Decadiene. Great. So if we count in from this side, 1, 2, 3, 4 carbons before we hit our double bond, versus this side where we have 1, 2, 3 carbons before we hit our double bond. We're going to start our numbering on this side where it's fewer carbons into the double bonds. We want the double bonds to have the overall lowest numbers associated with them. And when we give a number for the double bonds, it's going to be with the order of our counting, we're going to say the carbon number that the double bond starts at. So for this molecule, if we call this carbon 1, this is going to be 3, 5, 7, 9. This we would say 3 for our first double bond, because it starts on carbon number 3 and goes into carbon number 4. And we would say 6 for a second double bond, because it starts on carbon number 6 and goes into carbon number 7. Sweet. So, now I should have started this name at a different level so it didn't run into this molecule. That was stupid. I'm just going to shift that real quick. 3, 6, decadiene. Now we need to, let's name our other substituents on it really quick. We've got a 3-chloro. What would we name this? Does anybody know how we would name this?
Is it isopropyl?
It's not isopropyl because that's a bromine.
Would you just count another number, like 1, 2, 1 methyl, or 1 ethyl and 2 bromine?
Not like that either. It's a very interesting way. We're going to do it real concise, and we're going to kind of name this molecule itself. So what would we name this if we made the first attached carbon carbon number 1? This is carbon number 1, and this is carbon number 2. What would we name that? No, like if we just treated this whole thing as its own molecule. I can see that this is not a great example. But we could call it 1-bromoethane.
Yeah.
If we just had this on its own, it's a little redundant to call it 1-bromoethane. We just call it bromoethane or ethyl bromide. But if we were to super anally name it and call it 1-bromoethane, we can take that name, and just like we would take ethane and convert that to ethyl, we'll convert 1-bromoethane to 1-bromoethyl. So when we put that in the name, that's going to be, should be our first substituent, because that D should be 1-bromoethyl. We're going to put that whole name in parentheses. And then we're going to say where it is. It's on carbon number 4. So this is 4-1-bromoethyl. Cool? And that's how you get really badass substituents. Real badass ones. So we've got 4-1-bromoethyl, and the other substituents are easy. We've got the 3-chloro. And we've got a 6-isopropyl. I'm running out of room. 6-isopropyl. There's one last thing we got to do here, though. And part of it is make this isopropyl group smaller. We have to put in our E and Z designations, right? We've got double bonds. We need to tell the reader when they read the formula that we've written out, they need to be able to draw the molecule the same way we have. We don't want them swapping our chlorine and this ethyl group, because that would be a different molecule. That would be a completely different molecule. So we first need to figure out, all right, are these E or Z double bonds? So let's get our numbering for the carbon chain out of here. And I'm going to pop in some priorities. So if we look at this carbon, the chlorine is higher priority than the ethyl group here. We compare those two substituents. Chlorine outweighs carbon. And if we look at this side of our carbon-carbon double bond, well, each of them are attached to carbon. All right, womp womp. But this carbon is directly attached to bromine, who's super effing heavy. This carbon is just attached to some hydrogens and another carbon. So the bromine side wins. So our top priority dudes are on opposite sides. That means that this is E. So we can tell our reader, know, where does the E and Z go? Now that I'm thinking about it, I'm pretty sure it goes out front.
It goes in the front.
Yeah, it goes out front. We go 3E. Same way we would do chiral centers. 3E, comma. Now we got to look at our other chiral center. Not chiral center, but double bond. This one should be easier. We look at this side, carbon and carbon, drat. But this carbon has attachments to carbon and 2 different hydrogens. While this carbon is attached to 2 carbons and 1 hydrogen. Therefore, that dude wins. It's got more heavy stuffs on it. So we'll go down for top priority, and hydrogen loses to carbon. So we'll go here for top priority. They're on the same side, so that's Z. So we've got 3E, 6Z, 4, 1 bromoethyl, 3 chloro, 6 isopropyl, 3 6 decadiene. Woo! Look at that long name. Shit's crazy. Yeah.
Couldn't you just put the E and the Z where you put the 3 and the 6 for the decadiene? Because you're just saying the same bond.
Right? It seems redundant, but unless I am told, it's too far. Unless I'm mistaken, we do it that way, and I believe it's done that way kind of to mirror the R and S convention, because when we have R and S centers, we throw the name, we throw that out front. And as Dr. Faystate Guy loves to mention, they were published, all these rules came out in one paper, which he has a copy of somewhere. Managed to get a hold of it. Thank God. Let me just, let's see if I can find something.
I mean, you're probably right. It just sounds dumb.
I don't know. Frequently I'm wrong, though.
Please.
Yeah, right? Seems redundant, but I don't see it in here. In my glance through, but I'm pretty gosh darn sure we chuck that noise out front.
Do you think he'll give us a name like that and ask us to draw the structure?
Maybe. Probably not with this bromoethyl group in it. That was just me getting fancy. I wanted to throw a little spice at you. And show how to deal with that. Yeah, I'm not seeing how to mother fricker name that. Do a big sexy long name. Punk ass textbook writers. Not making things real easy for me right now. Cool. So the bonds, naming them. I feel like that's a pretty concise. You guys want to look at one more example, or any other things? Do you have any specific questions you showed up no? Any questions you guys struggled with on your own?
I'm looking at this worksheet from recitation. We didn't do anything for synthesis. Is that important?
Let's look at these actually. Yeah, thank you. Yeah. Juicy.
I think that was the last one we did.
I don't know how much he did briefly talk about synthesis in the end of class. At the end of class on Wednesday, I think, right? He was like, "Hey, synthesis, it's real important. I'm probably not going to talk about it ever until I test you on it."
Yep. Bowser.
Bowser? That's interesting. Yeah, I guess we'll kind of Bowser. So, yeah, we've got these fun synthesis problems. These are actually pretty tight. And we're given asked to identify the alkene we would use to make the products. These aren't super crazy rad, actually, but they're okay. So our first one is written, I wish you could use ChemDraw sometimes. It's so annoying to translate these written structures into actual drawings. So we're given this formula, and definitely helpful to actually draw that fricker out. So we've got a carbon, we can draw that 2 methyls on a carbon, a hydrogen, and an iodine. So that's what we've got there. And we're asked, what did we make this from? And so I'm going to use really cool, we usually use these retrosynthesis arrows. when we're doing a retrosynthesis. And when we do a retrosynthesis, what we're doing is backwards. Exactly. We're thinking backwards. We're thinking, all right, well, what could we have made that from? What could have come before this? Oh my gosh. Well, do you guys even remember a reaction that can add? Have we learned any reactions that we can use to add halogens onto a molecule?
HI on it?
Yeah, right? If we threw some HI, what would we throw HI at?
A double bond.
Right. If you threw HI at a double bond, we can add that iodine onto there. And so the only possible double bond molecule version, if we wanted to draw this without the double bond, we could say, we don't have the iodine there, we've got a double bond. Well, that should just be a propene. We can only draw a propene one way, real freaking convenient like that. Cool. So that is a very basic retrosynthesis. This reaction would be a hydrohalogenation. So we would do real cool hydrohalogenation, which, as we all certainly know, proceeds through a really rad carbocation precursor. Do this proton transfer nucleophile attack to get a carbocation. And we form the most stable carbocation, which is going to be the secondary one, not the primary. So the hydrogen goes to the less substituted position. The carbocation, the more, and now our iodine is ready. We've generated a really pretty good nucleophile. Iodine is not an amazing nucleophile, but pretty good. And a kick-ass electrophile. Now we're ready to generate our product. Next one, we're told to deal with 4-bromoheptane. Let's draw it. That's not heptane. That's heptane. 1, 2, 3, 4, 5, 6, 7. 4-bromo. 1, 2, 3, 4. Br. So if we wanted to generate this from an alkane, we still are going to do a hydrohalogenation. We want to add in just one halogen across a double bond. We'll be doing a hydrohalogenation reaction. And if we want to figure out what this came from, well, say, all right, we're going to kick that out and generate a double bond where it used to be. So this double bond could go on either side. It really doesn't matter because it would be the same molecule if I put it over here. We went through and named it. In either case, it would be 3-heptene. Another fricker. If I drew the double bond there, 1, 2, 3, it would still be 3-heptene. Nice little retrosynthesis, and this will follow the same mechanism, except here, if we were to do this reaction, we don't have control. This is not going to be a good reaction because neither one of these sites is really going to be preferred. So if we do treat this with HBr, we would generate this product by adding the Br to this side of the double bond.
Is it because when the double bond's kicked out, they're both secondary?
Exactly. When we break that double bond by attacking this proton, either carbocation we generate, there's 2 possible carbocations we can generate, and they're both secondary. So we could also end up doing a bromination at the 3 position. And yeah, that's because we could put a carbocation here or here. The intermediates would be carbocations at either the central carbon or the offset carbon, and both are secondary, so both have similar stability. Neither would be preferred. Good question. Question? Did I start talking about that? Whatever. Good point. It's a real good point. Let's look at the last one. All right. Chalk hands like, whoa. All right, so the last one, we've got CH3, 3COH. That's a T-butyl alcohol. So what double bond would we make this from? That's pretty easy to know what alkene we make it from, since there's only one possible structure we can draw. If we kick this out, and we want to make a double bond with this central carbon and one of the other carbons, well, they're all the same. They're all methyl groups, so it doesn't matter. This came from this dude, right? Yeah, that dude. 4 carbons and a double bond. And so what did we add to this? If we want to put an OH, we were talking about this earlier, into a double bond.
Put some water.
Water, and what else? We need a little something else. We can't use just water. Acid, that's right. We need water and just a little bit of acid. If we use too much acid, we end up having conditions that really favor the double bond, and that's not awesome. So if we use just a little bit of acid.
Do you have to put the double bond in the middle? Can you put it anywhere else?
Well, there's no real other way to draw it. Starting with this molecule, if I redraw this without the OH.
I mean, can you put the double bond like, I guess it'd be always in the middle. No.
Yeah, it's always going to be in the middle, since the dude in the middle is losing.
Yeah.
It has the leaving group getting picked off. Oh. I'm sorry I just showed up. I'm trying to wrap up.
Oh, okay. That's cool.
To the, but do you guys want to go over one more thing that's advanced? Let's talk about one more thing that's fun and complements what we talked about earlier. So we talked about earlier the acid-catalyzed, and we just looked at an example of acid-catalyzed hydration, or addition of an OH group. But we said that that's a crappy reaction, and that's because, just to redraw it, let's put you on a fun ring. So if we add H plus and H2O to this, in this case, with a non-symmetric double bond or an unevenly substituted double bond, here we're pretty much always going to, I don't have the double bond anymore, dummy. We used up those electrons to attack our proton. We're pretty much always going to put the proton on our lower carbon, because that will generate the more stable carbocation up here, and then our H2O. How is it going with this? Can attack that. Who then gets deprotonated by some more water to give us our final product. At the more substitute position. But like we said, this could interact with another equivalent of starting material, which would, again, behave as a nucleophile and attack our electrophile. So we could also, have this reaction occurring. And that sucks, because that's not going to give us our desired product. So there's a better reaction that we can use that will give the same product. It's 2 steps. It's called an oxymercuration demercuration. And it removes this carbocation intermediate and makes for a much cleaner reaction. So what goes down here, we don't use just water, although we do still have water in the mixture. Wait, we have water, right? Yeah, don't be a dummy. Dummy. So, just want to make sure I don't say anything wrong as I want to do. Ooh, whoa, whoa. Flip way too far. So, our first step, though, before I even, yeah, it's in base. Yeah, it's in base. I'm not even going to flip through it. It's in frickin' base. So it's 2 steps. Our first step, we have this really crazy mercury ion with some base. And our second step, so our first step is our oxymercuration. Our second step, we throw in some sodium borohydride, and we get our demercuration. And so the main takeaway from this is it does the exact same reaction. It gives us a nice Markovnikov addition at the more substituted carbon, but it gives a cleaner reaction. And again, it's because we don't have a carbocation intermediate. So what ends up happening here, sorry I wrote this wrong, there's supposed to be a 2 on this OAC. That's importante. So it is a mercury 2 salt. Really just the important part is that you have mercury 2 salt. So what happens is this guy goes ahead and generates one of those ACs, which is a acetate. One of these guys gets kicked out, it takes its electrons and leaves, and gives us a positively charged mercuric salt. And I'm going to draw the mechanism in really quick, or at least a part of it, because the whole mechanism is not actually known, which is fun. Mystery mechanism! So we have this dude, and this is our active reactant. This is going to find the double bond, and the double bond is our sweet electrophile, or nucleophile, sorry, remember. Double bond, nucleophile. This dude is positively charged. Should be a good electrophile. Metal salts are usually pretty good electrophiles too. So if we have heavy metals in there, or transition metals especially, not so much our first 2 rows of metals, but our transition metals, those guys are usually pretty good electrophiles. This gets grabbed, and we're going to generate not a carbocation, but this is going to primarily, the dominant species here, it's kind of like a carbocation. So our HG OAC is here, and it has a weak bond to this other site. This complex overall is positively charged. The majority of positive charge is located on this center. So my positive charge sign went off screen. And it's similar, very similar. We have similar conditions to when we had a carbocation. We still have a good amount of positive charge there. That site is still very...
HG...
Sorry, it's supposed to be HGOAC. I got a little overambitious with my A. Came in first. So it's the HGOAC, the acetate that's on there. So now, this is our electrophile, and it's ready for attack by this OH- nucleophile that we have in the mixture. So now our OH- can attack at this partially charged position, and that breaks this weak partial bond, giving us OH there and HGOAC. So So this is the product that we can isolate from the first part of our reaction. Nobody really knows how the second part of the reaction goes. We throw in the hydride, our sodium borohydride, and somehow it kicks out this HGOAC and replaces it with hydrogen. It's apparently believed to have some sort of radical reaction, but yeah, let's not dwell on it because people don't know how it happens. But we kick out the HGOAC and we replace it with a hydrogen. So we've had hydrogen 1 there all along. Let's just update this. We've got 2 hydrogens there. So this is a cleaner reaction, better reaction. It does the same thing as the acid-catalyzed addition, but better, without major side products. And that's kind of where I want to end. You guys have any final questions on that one? I don't know if you're going to be required to know that mechanism, but I think the more mechanisms you see, the better, because being able to draw them is real important. If you don't have Dr. Hill next semester, you definitely might need to know more mechanisms. Definitely might. It's definitely possible. I'll give you your John back. All right, thanks. Yeah, no problem.